Modern, high-speed jet transport aircraft have swept wings with relatively low thickness-chord ratios. For example, the Airbus A310 has a ratio of 12%. The overall value of CLmax for these wings is fairly low, and the clean stalling speed therefore correspondingly high. To reduce the takeoff and landing speeds and distances, various high-lift devices are used, increasing the value of CLmax. In addition to lowering the stalling speed, these devices, which principally comprise leading edge flaps and slats and trailing edge flaps, will usually alter the stall characteristics. From the 1G stall formula, it can be seen that an increase in CLmax will reduce the stalling speed. It is possible, with modern high-lift devices, to increase the CLmax by up to 100%. High-lift devices, which are fully described in the next set of lessons, decrease stall speeds and so minimum flight speed, enabling shorter takeoff and landing runs. This is their primary, and for airliners, their sole purpose. The EASA regulation 25.103b states that VCLmax is to be determined with the CG position that results in the highest value of reference stall speed. If the CG is in front of the centre of pressure, the CP, giving a nose-down pitching moment, as is usual, the tail plane must provide a download to maintain equilibrium, but the wing must produce more lift to balance the increased force of weight plus tail downforce. If the CG is further forward, it will produce a greater pitching moment, which must be balanced by a greater downforce from the tail plane. This in turn requires more lift to counter the downforce. From the 1G stall formula, you can see that greater lift gives a higher stalling speed, with the conclusion that forward movement of the CG increases the stalling speed. With landing gear up, the thrust-drag couple is not great, but when the gear is lowered, the profile drag below the CG is increased, which gives a nose-down pitching moment. This must be balanced by increasing the downforce of the tail plane, which in turn needs more lift to balance it. Any change of CG caused by a change in longitudinal position of the gear as it extends will have very little effect. The change in profile drag is far more significant, and the conclusion is that lowering the landing gear increases stall speed. Regarding engine thrust, the EASA regulation 25.103b states that VCLmax is to be determined with zero thrust at stall speed, and it is assumed that the aircraft is supported entirely by lift. If thrust is applied close to the stall, the nose-high attitude will produce a vertical component of thrust, which helps to support the weight, and less lift is required. Propellers will create an extra effect because of the slipstream. The most important factors in this situation are engine type, propeller or jet, thrust-to-weight ratio, and the inclination of the thrust vector at CLmax. With propeller-driven aircraft, the slipstream velocity behind the propellers is greater than the free stream flow, depending on the thrust. Thus, at low IAS and high power, the dynamic pressure within the slipstream is higher than that outside it, and generates more lift than at zero thrust. The lift at any given IAS or angle of attack will be significantly affected. For instance, if the aircraft is in the landing flare and power is reduced suddenly, the resulting loss of lift could cause a heavy landing. On the other hand, a potentially heavy landing can be prevented with a judicious burst of power. A typical jet aircraft does not experience the induced flow velocities of prop-driven aircraft, the only significant factor being the vertical component of thrust. This means that, since less lift is required to support the aircraft, there is lift in hand to decelerate to a lower speed. The effect on stall speed at high thrust can be large, but since there is no induced flow, the angle of attack at the stall will be very similar to that of a power-off stall. The conclusion for both categories of aircraft is that power-on stall speed is less than power-off. As an aircraft flies faster, the streamline pattern around the wings begins to change. Above about Mach 0.4, 4/10 of the speed of sound, the phenomenon of compressibility becomes significant. Mach 0.4 equates to around 300 miles per hour. Pressure waves generated by the wing's passage through the air propagate ahead of it at the speed of sound, and cause the air ahead of the wing to curve upward, or upwash, towards the low-pressure upper surface. At low speeds, the streamline pattern is affected well ahead of the wing, and the air has a fair distance in which to upwash. As speed increases, the wing gets closer to its leading pressure wave, and the air has less space in which to upwash, and so approaches the wing more steeply. The change in streamline pattern accentuates the adverse pressure gradient near the leading edge, and flow separation occurs at a lower angle of attack. Above Mach 0.4, CLmax decreases, as shown in the diagram on screen. According to the 1G stall formula, a drop in CLmax will increase the stalling speed. At a constant EAS, TAS will increase. Also, outside air temperature, or OAT, drops with increasing altitude, causing the local speed of sound to decrease. Mach number is proportional to TAS and inversely proportional to the local speed of sound, or A. As an equation, M equals TAS over A. At a constant EAS, Mach number will increase with altitude. The graph now on the screen shows the variation of stalling speed with altitude at a constant load factor. This type of curve is called the stalling boundary for the given load factor, in which altitude is plotted against EAS. At the load factor shown, 1G, the aircraft cannot fly to the left of this boundary. You can see that at lower altitudes, stall speed does not vary. This is because the Mach number at the stall is less than 0.4, too low for compressibility to have any effect. By about 30,000 feet, the Mach number has risen to the extent that compressibility is significant, and the rise in stalling speed is apparent. The conclusion here, then, is that stall speed will initially stay constant with altitude, but will increase with compressibility above about Mach 0.4. The various factors affecting stalling speed considered so far have been pretty much known quantities, explored during flight testing and promulgated in aircraft manuals. But contamination on the wing, particularly ice, frost or snow, can drastically affect the wing profile and affect the nature of the boundary layer, giving unknown and untested stalling speeds and characteristics. Let's consider the effects of these three main types of contamination, starting with ice. Ice formation on the wing will produce large changes in wing contour, particularly on the leading edge, leading to severe local adverse pressure gradients. High surface friction will considerably reduce boundary layer kinetic energy. These hazards cause a large drop in CL max and can increase the stall speed by up to 30% without any change in angle of attack. The extra weight of the ice will also increase the stalling speed, but the reduction of CL max is by far the greater effect. The effect of frost is more subtle. An accumulation of a hard layer of frost on the wing upper surface gives a texture of considerable roughness. Tests have shown that leading edge and upper surface contamination, with a thickness and roughness comparable to coarse sandpaper, can reduce lift by as much as 30%, increase stalling speed by 10 to 15%, and increase drag by 40%. Whilst the basic shape and aerodynamic contour of the wing are unchanged, the increase in skin friction reduces the kinetic energy of the boundary layer, and separation will occur at a smaller angle of attack and at lower CLs than a clean wing. The effect of snow can be similar to frost in that it will increase surface roughness. In addition, any deposit more than a light dusting can add significant weight and alter the aerodynamic profile. If there is any snow on the aircraft, it must be removed before flight. The idea that snow will blow off the wings during taxi or takeoff is a complete misconception, as has been tragically proved on occasions. Notably, the crash of a Boeing 737 into the Potomac River, Washington, in January 1982, which killed 78 people, and in which snow on the wings and tailplane was one of several contributory factors. The pilot in command is legally required to ensure that his aeroplane is aerodynamically clean at takeoff. It is vitally important that the time limitations, the holdover time, on any de-icing or anti-icing process are adhered to. If this time is exceeded before takeoff, the aircraft must be de-iced again. Guidance is available to pilots in the CAA's Aeronautical Information Circular number 106 of 2004, Pink 74, issued 11th of November 2004, entitled Frost, Snow and Ice on Aircraft. AICs are reissued from time to time, so you should check for updates. To summarize the effects of contamination, we can say that while the reduction in CL max with frost is not usually as much as with ice formation, its effect is probably more than may be expected from the comparatively smaller change in profile. The effect on the boundary layer's kinetic energy is a major factor influencing the separation of the airflow. The increase in stalling speed due to ice formation is difficult to quantify, as accretion rates and patterns and ice types vary greatly. Frost is a significant hazard, but will not form on upper surfaces in flight, although it does form under fuel tanks in a descent from a sub-zero high level into warmer, moist air, but this is usually of short duration. Snow, particularly wet snow, at temperatures not far below zero, presents a very serious hazard. All will affect stalling speed. The moral is that any contamination is too much, and none must be allowed to remain on any surface before flight. De-icing is essential.